All right, we're given this 2 by 2 matrix A, and the problem is in three parts. The first part says find all the eigenvalues of A. The second part is for each eigenvalue that you found in part A, give an example of an eigenvector that has that eigenvalue. And then the part C says find a basis for each eigenspace of A. All right, to solve this, let's look up here. We have this equivalence that we derived in the previous videos. And this is the definition of eigenvectors. And then this is an alternative form of this equation that's going to help us solve the problem. And so if you look, this is the homogeneous equation. Some matrix times V equals the zero vector. And remember I said in the last video that the zero vector is never an eigenvector. It's a trivial solution to this whole thing, and we never want to consider the zero vector as an eigenvector. So we want to be able to find non-zero v's that satisfy this equation. And we've worked with that before, right? This is the homogeneous equation, and what do we want? We want non-trivial solutions to this homogeneous equation. Because those non-trivial solutions v will be non-trivial eigenvectors if you just go back to this equation. So thinking about the invertible matrix theorem, remember that big long list of things that are either all true or all false. If you have non-trivial solutions to the homogeneous equation, what does that mean about the matrix? Well, it means that there's no free variables, right? Sorry, I misspoke. If you have non-trivial solutions, then you do have free variables. And if you have free variables, I mean, there's so many other things you could say. You could say the columns are linearly dependent. You could say the columns don't span Rn. You could say all these things. The one that we're going to actually use is that if you have non-trivial solutions to the homogeneous equation, then that means the determinant of the matrix is equal to 0. So if the determinant of A minus lambda in equals 0, if that's true about this matrix, if it is a 0 determinant, then there's going to be non-zero v's that satisfy this equation. And non-zero v's that satisfy this equation are non-zero eigenvectors, because these are the same equations, just manipulated algebraically. Okay, so that's the game plan. That's how we're actually going to identify these lambdas, finding the eigenvalues, is by setting the determinant of this matrix equal to 0 and solving for the lambda that makes that equation true. So then let's do that. So what is for this A? What is A minus lambda in? First of all, what is n? Well, it's got to be, these matrices A and lambda in have to be the same exact dimension because you're subtracting them. So this I has to be I2. It has to be the 2 by 2 identity matrix. So let's plug in. We have A, which is 3, 15, 1, 1. And we're subtracting lambda times the 2 by 2 identity matrix, which looks like this, right? So I'm going to say 3, 15, 1, 1. And then we substitute in, we distribute the lambda to each entry. So we get lambda, 0, 0, lambda. And then simplifying that even more, we get that the matrix A minus lambda in, remember I've been talking about how that's just some other matrix, and it is. It's equal to the matrix 3 minus lambda, 15, 1, and 1 minus lambda. This here is A minus lambda in. And as you do more of these problems, you're going to just jump straight from A to A minus lambda in. All you do is you just subtract lambda from the main diagonal. But I just wanted to show you where that comes from. So we have this matrix, and in order to find the eigenvalues of the matrix A, we have to set the determinant of A minus lambda in, this matrix, equal to 0. So let's do that. Let's set the determinant of the matrix A minus lambda in, which was this guy. Let's set the determinant of that matrix equal to 0, because when the determinant of that matrix equals 0, we have non-trivial v's that satisfy this equation, which means we have non-trivial eigenvectors. And so how do you do the determinant of a 2 by 2 matrix? You do this product minus this product. You guys remember. 3 minus lambda times 1 minus lambda minus 15 times 1, which is minus 15, equals 0. And then we're just going to do some algebra because we want to solve this equation for lambda, because then those will be our eigenvalues. So Really quick though, this here, the polynomial that you get by taking the determinant of a minus lambda in, that is called the characteristic polynomial. So that's a key term. So setting the characteristic polynomial equal to 0 is how you find the eigenvalues of some matrix that's given to you. So then we can just do some more algebra. This is just algebra 2, right? You just solve this for lambda. So I'm gonna like FOIL this and then refactor it and then see if we can get some solutions. So by foiling this, I get lambda squared minus lambda minus 3 lambda plus 3 minus, and then this minus 15 is still there, equals 0. And I can rewrite this as lambda squared minus 4 lambda minus 12 equals 0. This is factorable, right? You get lambda minus 6, no. You get lambda minus 6 times lambda plus 2 equals 0. And now we can find the solutions. We find the roots of the characteristic polynomial, right? The roots of the characteristic polynomial are your eigenvalues. So then we can say lambda equals 6 and negative 2. So we've done it. That's part A. In the next video, we're going to use the fact that we now know that the eigenvalues of A are 6 and negative 2. We're going to use that in order to get some eigenvectors by inspection, and then we're going to do like a longer process to get a basis for each eigenspace of A.